Okay. In the last class, we have started looking into how to use this Kmap technique to minimize logic circuits, right? And we also looked into a very simple recipe or guidelines so as to given a truth table, how do you use Kmaps to simplify the Boolean expression, right? So, just quick revision. A very simple guideline, which is circle all the rectangular blocks of ones in the map. So, the truth table, you have to focus on the output column. The truth table can have multiple outputs. You have to focus on the functional simplification of one particular output. So, the truth table or the logical expression is going to be designed for that particular output. Keep that in mind. Some problems might have multiple outputs. So, basically multiple output entries. So, for a given output entry, you have to create the Kmap and then put the corresponding ones in the, which is appearing in the truth table, to the Kmap grid, right, that matrix or a table that we are trying to create from the truth table. Okay. So, once you put all the ones there, you have to circle all the rectangular blocks of ones in the map using the fewest possible number of circles. So, all you are trying to do, you are trying to keep these circles that you are, or circles or squares or how, whatever you want to call it, right, as large as possible. You want to occupy as many ones as possible during that circling phase. Okay. And once you are done with that, maybe there is some other circle, some other one that is dangling outside, that could be grouped with other ones, other existing ones that has maybe already been a part of a circle. That doesn't matter, but whenever you try to put a new circle, at least one element has to be new. Okay. And read off the implicants that were circled. So, if you are circling something out, the implicant has to be checked off or tick marked or noted down. Okay. So, the Boolean equation is minimized when it is written as a sum of the fewest number of prime implicants. Okay. So, it is a fewest number of prime implicants. If it is written as a sum of that, then it is said that the Boolean expression has been minimized, and each circle on the Kmap represents an implicant. Okay. When you circle them out, let us say this is your Kmap, right, it looks something like this. I can use a let us say 4 variable Kmap, right. And remember of that gray code, once you write a truth table, we have a habit of writing them as 0 0, like if it is 2 bit 0 0 0 1, after 0 1 we use 1 0, which is 2, followed by 1 1, which is 3. That is a typical order which is followed in case of a truth table. But in case of Kmap, because we want to club those two successive variable and variables complement, we use something called a gray code, where only one particular bit is going to be flipped. Okay. So, if you are using, let us say, A and B on this side, which is 0 0 0 1, instead of 1 0, we are going to use 1 1. So, only this bit is going to be flipped, the other bit remains as it is. After that, there is again one more bit flip, which basically becomes 2. So, the first bit remains unchanged, the next bit remains, the last bit or the least significant bit undergoes a change. Similarly, here also you will do 0 0 0 1 1 1 1 0 and so on. Okay. So, what we are trying to say is that, let us say you have again kind of revising, if you have, let us say 1 1 1 1, and let us say there is one more 1, and here you have a 0, right. So, what you can do is that you can possibly circle this entire thing. This is one, but the right hand side one is still dangling. So, this could be also circled with yeah, I think there is some issue with the, yeah. So, this is one group, right, and this is the largest possible circle that could be drawn here, assuming that the remaining ones are all probably zeros. okay, you can't do anything there, right. So this is one possible circle. The other one is you can only form something like this using the dangling one. So that could be clubbed with an existing one and made as a bigger circle, right. This 2 element circle and this 4 element circle. So once you do this 4 element circle, you should also read off the implicants. So in this particular case, if this were C and D, so if you look at the across the column, so 0 0 and 0 1, so D basically vanishes. So you have D and D complement, right. Sorry, this is, I think I missed out one of these lines. So 0 0 0 1, right. I think because there was an erasing effect, right, I lost track of one line. So this is something that did not change, C bar, and this is something that changed from D to D bar to D, right. 0 was constant, it did not change. So this is C bar from these columns, and if you look across the rows, here you have 0 0 and the next entry is 0 1, okay. So 0 0 here is A bar, B bar, and this one is A bar, B. So what did not change was A bar. So B changed from B bar to B, which is unified, okay, and eventually vanishes. So this square or a circle that has these 4 entries become A bar, C bar, right. And here if you see, so this basically becomes A bar, C bar. Here if you see the other circle that has these 2 components, here you have one entry which is A bar B and the next entry is A B, right. So one is A bar B and the other one is A B. So as you can very clearly see that B remains unchanged across these 2 things. A bar and A gets unified and eventually vanishes. And if you look at this particular row is 0 1, which is 0 1 means C bar and D, okay. So C bar, D, and then you have from the top side, right, you have A bar vanishes, so this is only B, okay. So this becomes B, C bar, D, okay. Just a quick recapitulation of what we have already studied in the last class, right. And just make sure that you have the sum of the fewest number of prime implicants, that means the Boolean equation or the expression is minimized, okay. So there are some Kmap rules, the rectangular groups of size 2 to the k for any integer k. So each cell, so these are the rules that tells you that how can you circle or put these rectangles or circles in these Kmaps. This has to be rectangular groups, right. You cannot really do something, maybe I will show you here, which is kind of illegal, right. I will use a blue color this thing. So you cannot make a group like this is illegal, okay. This is not allowed. You have to make rectangular groups, so it has some width, right, in terms of the number of bits and some height, width and height, and then you have to circle off that entire thing, okay. So circle groups of size 2 to the power k for any integer size k. Each cell has the same value, they have to be 1, right. But you can, depending on the kind of minimization you are interested in, you might be interested to filter out the zeros, and you can do accordingly in the dual form, okay. If you are really wanting to simplify the expression for 0, there is no direct reason to do that, but you may have the necessity, and Kmap only provides you the tools to simplify the expression. How you are interpreting it is a different thing, okay. And note that all values must be adjacent, and apart from the wraparound case, which is sometimes you may have, as I told you, situations where this part of the map, right, can be considered as adjacent to the, so this is your like column 1 and this is, let's say, your column some n, right. So column 1 and column n are also adjacent because of the way we code them in terms of the gray code, right, the way they are done in case of 2 bit 0 0 0 1 1 1 and 1 0. So 1 0 is adjacent to 0 0 in terms of only 1 bit flips. Okay, this is adjacent. Okay, so that is another thing is called wrap around. Similarly, we can also wrap around the top row. So this is if it is row 1 and if this is row n, this could similarly be wrapped around. Okay, so this is something where we typically make mistakes. We need to remember that this wrap around is very important for the Kmap to create an optimal solution. And how does a group become a term in an expression? Determine which literals are constant and which varies across the group. This is also very important. The exercise we have done just now was trying to see which of the variable is actually vanishing. Vanishing means you have both in the group, you have both a and a bar, or you have both c and c bar, b and b bar, right, the variable as well as its complement. Okay, so which literals are constant and which vary across the group. Eliminate the literals and then add the constant literals. Okay, so if we are using the constant 1, then we use x. If you use constant 0, you use x bar. Okay, for now we will just assume that we are working with only ones, we are not working with zeros. So if you have groups where x and x bar are both present according to the gray code, you have to make sure that they are eliminated, and for the variables that remain you have to use an ANDed AND of those literals, right. That is something that we have already shown as an example. And the biggest groupings, what is a good solution? The biggest groupings eliminate more variables or literals in each term. So bigger is the size of that rectangle, the better is your elimination, because if you have adjacent terms next to each other, they are going to cancel out. So it is very important to make the group as large as possible, so more of the variables are eliminated, right. It's a way to guarantee that. And then you have fewest groupings. If you have too many groupings, then you have like each one of the groupings are going to create a minimized expression, but since you have many groupings scattered around, they might not be optimal in terms of the number of gates. Okay, so you have to remember that the final expression that you are going to have a sum of this implicants, right. The sum of the implicants that you are going to get is going to be needs to be implemented in the fewest number of gates. So it is better to have the circles or the groupings as large as possible. So or together all the AND terms and you create from individual groups. So you have like small individual groups that you are circling around. Each one is going to create a literal, each one is going to create an implicant for you, and all you are doing is basically ORing or summing, right, like logical plus those AND terms. Okay, so that is basically the final output or the simplified result of the expression that has been given to you, and you are using this Kmap to simplify them. Okay, so now we will come to a more involved example. This is going to have we are going to have two reasons to do this. One is that it is going to revise a little bit involved circuit. We will understand the design, and after doing the design, truth tables and so on, we are also going to see that how to minimize the circuit using Kmaps. Okay, so I gave you an example of this comparator, right, very early in while we introduce things like combinational logic circuits. I will like go back and kind of quickly show you, right, what we have studied earlier. So if you remember, comparators was one of the standard building blocks, right, and these comparators were used to compare two bits. There are many interpretations that we had already discussed earlier, and based on every interpretation your circuit design is going to change, right. One could be if x is greater than y, you want to show some result. If x is lesser than y, you want to show some result. If x equal to y, you want to show some result. But depending on how many bits you are having available for output, that will restrict the number of different things that you can show, right? So if you are having only 1 bit output, we were discussing a case, for example, I can output 0 when x is greater than equal to y. I can output 1 when x is less than y, strictly less than y. This could be 2 cases, but you can come up with like various kinds of cases and develop a circuit for that, right? And we have studied this XOR function. From here we extended it to create a half adder. We also looked at how a full adder works, right? So this kind of discussion has already been done, right? We have discussed all these things, and I just wanted to refresh your memory that while we studied this equality comparator, but you can always use this for not just equality comparator, you can also use it for detecting which one is greater, which one is smaller, and so on. This kind of things can also be done. Okay. So we also asked this question about how about comparing two n-bit numbers, right? If you have two n-bit numbers, if you want to do a equality checking, what exactly you should do. Okay. So in this example, I think we went over this, did a truth table and so on. I think we asked you to also create the circuit and modify that and so on. So modify that based on the input or the output requirements. So a greater than equal to b should be a 0 output, whereas a lesser than b is going to be a 1 output. So it's better by this time, hopefully you have started practicing this kind of exercises, which is a fundamental building block of a processing unit, right? So this kind of circuits are very commonplace inside a computer processor, which is a CPU. Okay. So now I will go back to where I left, right, which is the Kmaps, right? And the last thing that is remaining now is how to use a Kmap in a real example. So this is a 2-bit comparator, and this 2-bit comparator is going to have these two numbers. The first number is a 2-bit number AB, and the second number is another 2-bit number CD. And B, as you can see here, is the least significant bit. A is the most significant, with only 2 bits. And if AB is equal to CD, we should trigger F1. Okay. So there are 3 outputs, F1, F2 and F3. Note that earlier we were kind of indicating that there is only one output. Here there are 3 outputs. If F1 is being set to 1, in that case A and B, AB and CD, they are like equal. Okay, these 2 bit numbers are equal. If AB is less than CD, we are going to trigger F2. Okay. So and then for the third case, which is the remaining case, is AB is greater than CD. So in that case we are going to trigger F3. So note that one of the outputs is going to be true. If F1 is true, F2 and F3 has to be false, and likewise for all the different outputs. Okay. So what's the first thing that we should do? We should draw a truth table. Okay. And what are the different columns the truth tables are going to have? The truth tables are going to, of course, have 2 parts. One is the set of inputs, and the other one on the right hand side you are going to have the set of outputs. In the set of inputs, the different columns that we are going to have are A, B, C and D. There are 4 inputs, and on the output side there are 3 outputs, F1, F2 and F3. These are the 3 different outputs. And how many rows you are going to have for what are the various combinations of inputs A, B, C, D? We are going to have 2 to the power 4 or 16 different combinations of inputs. Okay. And for every such combination, one of the variables, right, one of the output variables is going to trigger, right. So either whatever be the value of AB or CD, either they are equal, or AB is less than CD, or AB is greater than CD, right. There is nothing else possible. Okay. So just make sure that you understand that. So F1 or F2 or F3 has to be 1. right, and one of them will only be 1, at most one, not at least one of them, at most one of them has to be 1. So this is just for sanity checking your entire circuit, your truth table. Okay. So we are going to design a 4 variable Kmap for each of the 3 output functions. Okay. So now let us look at the truth table. This is also an important exercise, not from the perspective of the Kmap only, but also how to design these circuits. We have went over several examples, but this is a little bit more involved example. We are solving it end to end. So I guess it is an important exercise also to give you more insights on such designs. Okay. So let us go one by one. As I told you, there are total of 16 different rows for various input combinations. You can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. And all the 16 combinations we are representing in an incrementing order. If you are representing this A, B, C, D as a binary 4-bit number, it is as if going from 0, 0, 0, 0, which represents the binary number 0 or decimal number 0 rather, to 1, 1, 1, 1, which is decimal 15, right. So there are total 16 different elements, right, 16 different unique input combinations. So for every such combination, let us say F1 is triggered in this case. Why? Because both of them are 0, right, AB is 0 and CD is also 0, so F1 is triggered. Okay. Similarly, since it is a 2-bit number, AB or CD can also only be 0, 1, 2 and 3. So let us look at where they are again equal. They are again equal here. Both of them are 1. So F1 is triggered, and make sure that okay, F2 and F3 are off, right. Similarly, if you can go to 2, so this is 2, AB is 2, CD is 2, F1 is triggered. They should not be triggered because those cases or those conditions do not arise. Similarly, when they are 3 again, similarly we have this thing. Okay. So if you want to design the circuit corresponding to the function F1, you do not have to do anything else. Okay. Because whatever is required for designing the circuit for F1 is all the literals or all the implicants are prime implicants, right, we are in front of our eyes. Okay. Which is the 4 min terms, right. If you want to write in form of min term, this is nothing but summation. If it is a sum of products, min term 0, right. This is 5, comma, this is 10 and 15, right. Why 5? This is 0, 1, 0, 1. This can be represented as the 5th min term, and 0, 1, 0, 1. They are equal, right. So that is why 5, 1, 0, 1, 0. Like both are 2, 2, but here we are representing as the 10th min term. 1, 1, 1, 1, 3 and 3, both of them we are representing as the 15th min term. So if you are only trying to find out as a simplified version of F1, this is good enough. Okay, we are going to come to the rest of the columns later, but let us try out this thing, right. So we have written AB as the row entries here. These are all standing for the various combinations of A and B. Of course, in the gray code format, I will specifically tell you to for you to remember this. Okay, this is very important, otherwise you cannot group them. So there are many times we come across students who instead of having 1 1, they will do a 0, like 0 1 and then 1 0 and then 1 1, right. So the groupings won't make sense, right. You need to understand why you can't do that. You are grouping something and cancelling things out, but 0 1 and 1 0, you cannot really take anything common and cancel the other thing out, right. That unifying theorem won't work. For example, this is let us say A bar B, right. This is AB, but in that in case you are using 1 0, 1 0 stands for AB bar, right. You cannot take A bar B and AB bar and cancel one of them out, right. That is not possible. So that is the reason you need to keep in mind that you really need to follow the gray code scheme, gray code format. So now we'll start with a 1. 1 is already there for all of them being 0. So it is A bar, B bar, C bar, D bar. This is ticked off. Then I put this entry which is A bar B and C bar D, 0 1 0 1. Then it is for the 1 1 case 1 1 1 1, AB is equal to 3 and CD is equal to 3, and the next case is AB bar which is 2 2. Okay. So there is no more mean terms that are available, unfortunately. So all we have to do is just proceed with the writing the mean term expressions and adding them up. Okay, so there is only thing is that we have to write down those values individually. I have shown this arcs for indicating the groups. So if you are talking about the last group here, right, if there are two things that arrive here or appear here, right, D and D bar is going to be cancelled out. So 1 1, so this is C. If this is the group, right, this would have been C bar. Okay, this is C, right hand side C bar. Similarly for A, B, C, D, A bar, B bar, C bar, D bar, same principles apply. Okay, so this will be, as you can always understand, A bar, B bar, C bar, D bar, then you have all these 4 things. Okay, there is no chance of simplification because you cannot find out any rectangular groups. Okay, so this was not very interesting because Kmap could not be applied in the sense that we wanted to use this Kmap for simplifying the expression further. We were not able to do enough justice. Okay, so now let's look at the expression for F2. We want to validate that first. So F2 was supposed to be coming when I think, let me quickly check, AB is less than CD, right? So CD is greater. So if CD is greater, let us look at F2. So they are equal, of course. This will not come in F2, but here CD is 1, 2 and 3, right, which is greater than 0. Okay, so of course these 3 are all ones. Whenever it becomes AB becomes 1, so here AB has become 1. So 0 is less, so it won't be applicable. This will be applicable for F3 though, right? 0 is CD is now less than AB, that is F3, and the other cases they are equal, this will trigger, and this one will be greater. Okay, so this is 2 and this is 3, which is greater than 1. Okay, so here F2 will trigger. In the next examples also it is pretty much the same. This is again 2, and here 0 is lesser than 2, so this will trigger. 1 is lesser than 2, this will trigger. 2 is equal to 2 here, so this will trigger, and 3 is greater than 2, so this will trigger. Okay, here CD greater than AB. Okay. If you want to go to the next term, next set of rows, which is AB is 3. So mind that I am writing the value of AB. So here AB is 3. So all of them should be either less or equal to, because you cannot go to 4 using 2 bits, right. So 0 0, of course it is lesser here. 0 1 is 1, this is lesser. 1 0 is 2, lesser. 1 1 is 3, 3 equal to 3, this, right. So you do not have any this thing here. Okay, so these are all zeros. Okay, so hopefully you have understood how to draw the truth tables for any of these such problems, be it whatever kind of circuit is required. As long as you understand the functional specification properly, you can always convert this into a truth table, and whatever be the required number of your outputs can be done like that. So currently you should be all clear with all the rows and columns with the truth table. In the truth table, In the previous exercise where we wanted to simplify the Kmap for F1, it did not appear to be having any structure that will help us for further simplification, but whereas we can have a lot of terms here for F2. So, let us try for F2, right. So, for F2, as you can see, we are taking chunk by chunk. So, first we are choosing AB is equal to 0 chunk. So, this is the first chunk, and the chunks I have kind of marked with this red color dotted line. So, there are 4 chunks, and we will put the terms chunk by chunk. So, the first chunk, which is both AB is equal to 0, which signifies the first row. So, all the rows here is like AB is equal to constant. So, in this case AB is equal to 0 0, which is decimal 0. These are the 4 columns that we have to fill up. We are filling up every column except CD equal to 0 0, right. C equal to 0, D equal to 0, this is not being filled up, right, because I have a 0 for that particular entry. The rest are 1, this is 1, this is 1, this is 1. So, we have put 1, 1 and 1. Let us look at the next row. The next row is AB is equal to 1, which is A equal to 0, B equal to 1, 0, 1, this one. Here we have the first two 0, 0 CD, 0, 1 CD is equal to 0. So, this will be 0, this will be 0, and these are the ones that we have. These two are ones. Next, if we go to the A equal to 1 1, which is the last chunk where A is equal to AB is equal to 1 1. Let us look at F2. We do not have anything, right. So, F2 there is no such values that we can pick up in this particular case, right. So, this will likely be zeros. Next is okay. So, AB, just a minute, this is for F2, right. There is some issue with this. A is equal to 1 1, A is equal to 1 1, and okay, I think there is an issue here. We are not going to count this, because for F2 CD is equal to 1 1 and AB is equal to 1 1, this is not going to be counted. This ideally should be 0. We will like take care of this typo. So, the first block, if you have this rounded rectangle that has these values, right, 1 1 1 1, that becomes A bar C. So, why it is A bar? This vanishes out, this is B bar and this is B, and this is A bar, right. And if you see here, this is C, as I told you, across this row this is C, because D bar vanishes out. So, A bar C. So, for this particular typo, we should have, actually this is a mistake of the slide. You should look at the annotated slides here, that is what I am teaching now. So, this is the same kind of mistake that we are almost prone to doing here also, that is there. So, A 1 0 has to be chosen, right, 1 0, and in 1 1 this is 1. So, ideally 1 0 is the A's row, right. Now, instead of here 1, we should have a 1 here, okay. So, 1 0 is the last entry, which is going to be 1 if CD is equal to 1 1. So, rest are all zeros, okay. So, if you want, you can count the total number of ones, 1 2 3 4 5 6, here 1 2 3 4 5 6. So, there are 6 ones in F2. This is the distribution of that, just ignoring the fact that I mistakenly have swapped this one, right. So, it is very tricky. If you put a 1 here and accidentally merge this thing, this won't make any sense, right. So, this is a small typo, just I will put a revised slide for your reference, okay. Here you can group them again. Here this is going to be C bar D, this is CD. So, D is going to remain, C and C bar are going to kind of crossed out, unified, and as you know, this is the row for A bar B bar. So, A bar B bar D, right, C vanishes out, and this is the wrong grouping. This is not something that should be done, because A B 1 1 and C D 1 1 does not produce this row. So, this is a mistake. Okay. So, ideally there won't be any grouping here. This is just going to be an isolated term that is going to be done here. So, we do not have this term, we are going to have an independent. So, this grouping is not going to exist, because that is going to be 0. Okay. So, we are going to have plus A B bar C D. Okay. This is going to be the thing, right. It is not B bar C D, but A B bar C D. So, just mind the mistake here. There was a minor, it is actually not a minor mistake, it is a major mistake, because the position of the terms, the position of this constant inside the Kmap really matters. Okay. So, in the same way, I think you should be able to mark out the various zones for F3. I will at least help you with putting those numbers. I will just use the green color for F3. So, if I put a green color 1, that means that is for F3 here. So, as you can see, the first rows are all zeros. So, it is ideally going to be 0 0 0 0 for F3. So, green is equal to F3 I am mentioning. Next one, you will see the row for AB, AB is equal to 1, which is 0 1, and here you have only one entry that has a 1, right. So, 0 0 CD, this is going to be a 1, rest are all zeros. Next we come to the this row, which is AB is equal to 1 1. This is where I made a mistake for F2. Hopefully, we will not make a mistake for F3. So, 1 1, we are sticking to this particular column, and here we have 1 1 1, right. 3 things are 1, 0 0 0 1 and 1 0. So, 0 0 CD, 0 1 CD, right, and 1 0 CD, right. 1 0 CD, the other one is 0. Okay. And the last column is 1 0, which is here, 1 0 is AB, this is the last row, sorry, for AB is equal to 2, which is 1 0, and here you have 3 entries that are marked as 1 for F3, which is respectively CD is equal to 0 0 and CD equal to 0 1. So, CD is equal to 0 0 is here, CD is equal to 0 1 is here. Okay. Again the rest are all zeros. So, this is going to be the structure of the Kmap, and then you are free to circle them, right. For example, one circle could be this. So, this is the largest possible rectangle here. Then you can potentially have one more. So, the idea is this, right, you want to create the largest circle as possible and as few total number of circles as possible, right. If you follow these two things, it should be helping you to create the optimal or minimized Boolean expression. Okay. Then you can potentially have this, right, and then you have more terms. One of these things could be done, right. So, you can take this and also take this and create a simplification. So, I would request you to come up with the expression for this groupings, right. So, here you have the 4 4 implicants in this group that we have created, this larger one, which is going to be see B is going to vanish out, V bar and B. So, you have A, and in this end you are going to have C bar. So, some A C bar will be there. Okay. Then find out the 2 other groupings and then add them. So, this is going to be the simplified expression for F3.